Consider this ordinary differential equation y double dash plus p of t y dash plus q of t y equal to 0. Well, two functions, y1 and y2, y1 of t and y2 of t, are a fundamental set of solutions I will use this fundamental set of solutions for short of this equation 1 if two conditions are satisfied. y1 and y2 are actually solutions of 1, are solutions of 1. Number 2, every solution y of t of equation 1 can be written as a linear combination of y1 and y2, which means it can be written as y of t equal to a certain constant c1 multiplied by the first solution, y1, plus a constant c2 multiplied by the second solution, y2. There is a relatively easy way of checking if two solutions form a fundamental set of solutions, which is provided by the following theorem. So two solutions, y1 of t and y2 of t form a fundamental set of solutions if the determinant the following determinant, y1 of t, y2 of t, y1 dash of t, y2 dash of t, is different from 0 in the interval we are considering. This determinant is actually called the Wronskian of these solutions. So Wt is this determinant, which is called the Wronskian. So two solutions will be a fundamental set of solutions if their Wronskian is different from 0. So in this example, we want to show that y1 equals sine t and y2 equals cosine t form a fundamental set of solutions of this equation here. Let's call this equation 1. So first we need to check, we'll do this in like 3 steps. First we need to check that y1 is a solution. y1 is a solution of equation number 1. y1 is sine t, y1 dash is cosine t, and y1 double dash, the derivative of cosine minus sine t. And this, of course, that means y1 dash plus y1 is minus sine t plus sine t, which is equal to 0. So yes, y1 is a solution of equation number 1. Second step is we need to do the same with y2. So is y2 a solution of 1? Same thing, so y2 is the cosine of t. y2 dash minus sine t, and y2 double dash second derivative is minus cosine t. So that means y double dash plus y2 is minus cosine t plus cosine t, which is equal to 0. So y2 is also a solution of equation. Now they're both solutions. Now I want to check that they're actually a fundamental set of solutions, and I can check that by finding their Wronskian. Is it different from 0 or not? So let me just recall that this is y1, y2, and then y1 dash and y2 dash, like this, which is, in this particular case, y1 is the sine t, y2 cosine t, the derivative cosine, the derivative minus sine. I want to find this determinant. Of course, it's the multiplication of these two minus the multiplication of these two. So it will give us minus sine squared t minus cosine squared t. And I can simplify this into something like this. And of course, sine squared plus cosine squared is 1. So this is minus 1, which is of course different from 0. So y1 and y2 are a fundamental set of solutions for the equation number 1. Now I want to complete this example by finding the general solution of equation 1, the general solution of our equation 1. Well, because y1 and y2 are a fundamental set of solution, that means the general solution will be y equal c1 multiplied by y1 plus c2 multiplied by y2. So therefore, y will be c1 multiplied by sine t plus c2 cosine t, and that is the general solution of equation 1. In this example, we propose to solve an initial value problem in the following way. First, we want to check that this solution and this one form a fundamental set of solutions on this interval minus infinity to 0. So the variable t is in this interval. From this fundamental set of solutions, I want to build the general solution of the differential equation, and finally, I want to solve the initial value problem. So let's first check that y1 is a solution. So I want to check that this function is a solution. So y1 is that, so its derivative will be 3t squared. Its second derivative will be 6t. Now, if we substitute in the equation, so t squared y1 double dash minus t y1 dash minus 3 y1 will be t squared multiplied by 6t minus t times 3t squared minus 3 times y1, which is t to the power of 3. And this will give us 6t to the power of 3 minus 3t to the power of 3 minus 3t to the power of 3, which is equal to 0. So, yes, y1 is a solution. Next, we will check that y2 is a solution. So y2, which is minus 1 over t, then y2 dash, the derivative is 1 over t squared, and its second derivative is minus 2 over t to the power of 3. So we substitute into the differential equation t squared y2 double dash minus t y2 dash minus 3 y2. This should give us 0 if y2 is a solution. Well, let's check that. So this y2 dash is minus 2t to the power of 3 here, minus t 1 over t squared minus 3 times minus 1 over t. And that is minus 2 over t. This is minus 1 over t. And this is plus 3 over t. And of course, this is equal to 0. So, yes, y2 is a solution. Now, the next step then is to check that these two solutions form a fundamental set of solutions. So that's now a question. y1 and y2 form a fundamental set of solutions. And we will check that by looking at their Wronskian. y2, y1, y2, y1 dash, y2 dash. This Wronskian, is it different from 0? Well, let's check that. So y1 is t to the power of 3, y2 minus 1 over t, the derivative and the derivative. Now, to calculate this, of course, we do this multiplication minus this one here. So that will give us t plus 3t, and that will be 4t, which is of course different from 0 if on the interval minus infinity to 0. Okay, so yes, y1 and y2 form a fundamental set of solutions. That means we are now able to write the general solution. So the general solution is y equal c1 y1 plus c2 y2. So it will be y equal c1 multiplied by t to the power of 3 minus c2 or plus c2 multiplied by minus 1 over t, and that is the general solution. We will now solve the last step of this problem, which is finding the solution of the initial value problem. Well, we have the general solution, which is y equals c1 t to the power of 3 plus c2 minus 1 over t. That means y dash is 3 C1 t squared plus C2 1 over t squared. Well, the initial value problem says that y of minus 1 is equal to 0 and y dash of minus 1 is equal to minus 2. So let's substitute. If we substitute in 1, then if we put t equal minus 1 there, we get C1 minus 1 to the power of 3 plus C2 minus 1 over minus 1 here, and that's equal to 0, which means minus C1 plus C2 is equal to 0. That's the first equation we get. If we substitute in equation 2, then we get, of course, 3C1 minus 1 squared plus C2 1 over minus 1 squared, and this is equal to minus 2. So that means 3C1 plus C2 is equal to minus 2. So we have now two linear equations. So let me write what we have here. So we have these two linear equations. C1 plus C2 is 0, and then 3C1 plus C2 equal to minus 2. We want to solve this. Well, the simplest way is to just subtract, like this first equation minus, so we can cancel the C2s. So we get minus 4C1 equal to 2. So C1 equal to minus half. And then, of course, if we take this here, then we will get that C2 is also minus half. So therefore, the solution of the initial value problem is y equal to minus half times y1, which is t to the power of 3, and then plus c2 multiplied by y2, which is minus 1 over t. And we can simplify a little bit this, so it will be minus half t to the power of 3 plus 1 over 2 t, like this. So that is our final answer.